This lecture is about the fundamentals of statistics. I've made a little overview of the things that we'll talk about in this lecture. First, I want to talk to you about validity. This is a little bit sort of building on the presentation that Berenike gave this morning, ways in which you can evaluate your experimental design. Then we'll go into the theory behind statistical testing, the principles behind testing, if you will, that you need to know in order to make the right choice for the statistical test that you need to answer your specific research question. Key terms that we'll talk about in this lecture will be errors, probability, significance testing, and regions of rejection. And I will use the example case study, so Anna and Don's study, throughout this whole lecture. Okay, so first, validity. Like Berenike showed you this morning, there are a lot of choices that you have to make when designing your experiment. Those choices also influence, in the end, what kind of statistical tests that you can carry out later. So as you are designing your experiment, you have to be really aware of every possible negative consequence that your choices in experiment design can have in the long run. So the awareness of the pitfalls of your design or of other people's designs comes with evaluating the validity of your design. Okay, so validity basically refers to the degree to which your experiment allows you to make claims about the relationship between the variables in your design. It is also the basis on which other researchers evaluate your experiment as well. It's important to estimate to what degree the conclusions that you draw from your results are valid. Because it's the basis on which other researchers evaluate you, it's always it's really important that you always explain the choices that you've made in your experiment design in excruciating detail. It's for them to try, like if they want to replicate your study, they need to know all of the information about the choices that you've made, but it's also necessary for them to be able to evaluate the validity of your design and your results. Now, there are three types of threats to the validity of your design that you need to be aware of. So those are the threats listed down there. Threats to internal validity, threats to external validity, and threats to construct validity. And I will go through each and every one of them and give you some examples. So, what is internal validity? Your experiment is internally valid when the relationship between your independent and your dependent variable cannot be explained by any other variable. When we can be sure, in other words, that the results are not due to interference of some uncontrolled factor. Now, threats to internal validity are, for example, and we've touched upon a couple of them this morning already, are the influence of extra experimental factors. So factors that lie outside of your design and also mostly outside of your control. For example, you are conducting a longitudinal study on the effects of reading a novel about Islamic culture on the degree of tolerance that people exhibit towards refugees coming from Islamic countries. Like, this is an example that obviously is very relevant to the situation right now. And I've seen some studies being designed right now to sort of tackle this particular issue. However, then over the course of that experiment, over the course of that longitudinal study, what happens, for example, is a terrorist attack in a European city. Obviously, you could not have foreseen that that would happen over the course of your experiment. But this might well have influenced your participants' opinions on refugees coming from Islamic countries, apart from the treatment, so the novel that they read in your experiment. So even though this is totally outside of your control, I'm not saying that you should control whether or not there's terrorist attacks being carried out. It is important to note these things when you're writing up your results, to note that all of the possible sort of factors that could have influenced the results in your experiment. It's important to do so that other readers that read your papers then can decide for themselves how much of an influence this actually had on your results and whether that is acceptable to them or not. Another threat could be incomplete experimental design. So forgetting to include possible intervening variables, not including a control group, not including a pretest, not using any randomization, those could pose threats to internal validity as well. And then the last one, or the last one that I put down here, if you look into the book, The Scientific Methods for Humanities from Peer and al., they have a complete list of possible threats to internal validity, but I think these are the most important ones. The last one is test effects. So test effects can occur when, for example, you pretest sensitizes your participants to some aspect of your treatment. For example, a questionnaire about how empathic they are when reading before the treatment might make them aware that the treatment is there to increase their levels of empathy. Which then might lead them to fill out the post-test questionnaire differently, not because of the treatment, but because of the test, and they were made aware of the treatment already, so they are adjusting their responses accordingly. There are different ways in which you could address this problem, mostly involving more complicated designs, so having different control groups in there. So I think on pages 140 until 142 of the book, you can find different ways in which you could sort of deal with these threats to validity. Another threat in that sort of category is ceiling effects, which we also talked about before already. And these can occur when you ask people about issues that people feel very strongly about, no matter what kind of treatment. For example, if I would ask you guys, so the group of people sitting in front of me, do you think it's important that kids read? On a scale from 1 to 7, we will probably find pretty high scores in this group overall, even if we could divide you into a control group who doesn't get any treatment and a group that does get a treatment, namely an article about the importance of literary education, for example. Probably the two groups will still score really high on this scale from 1 to 7. So what you could do to deal with that is you could enhance the sensitivity of the questions. For example, instead of a scale from 1 to 7, you could use a scale from 1 to 100, for example. This would obviously cause problems of a different kind as well. So what I think would be the best way to deal with it is to pilot test your questions always and try different formats in these kinds of things, or to basically take different samples, not just use a sample of people that you know will already respond to this question in a certain way, but sort of diversify your sample. I think pilot testing in any case is always a good idea if you're not working with established measuring instruments. So you can test out different ways in which people could respond to your questions that you might not have foreseen beforehand. Okay, external validity. Your experiment is externally valid if your results can be generalized to a larger audience. So if we can find the same effect that you found within your study in the real world, so to say. Interaction effects, so these are, again, threats to external validities. The first one would be interaction effects between selection and treatment. So the example that I just gave about this group of people responding homogeneously to the question of, is it important that kids read? That is a good example of that kind of threat. So if I would study people's opinion on the importance of reading for kids and I want to generalize the results to a larger audience, I should use a sample of participants that is representative of the whole population and not just of people working with literature or within literature. Okay, so another threat would be the situation. For example, conducting an experiment in a school class environment might make it feel like a test to the participants, which makes it hard to generalize the results outside of the classroom. Or when you let people read a book in the lab and measure their levels of absorption, which is something that I deal with on a daily basis, this might not exactly correspond to their absorbing experiences that they have in daily life, because they feel like they're being watched while they're reading because there's somebody in the lab. Or they're sitting there with a whole group of people, but that's not normally how you would read a book when you're sitting at home. Or the example of the terrorist attack that I gave earlier already. This would also be a threat to external validity because people in other parts of the world outside of Europe might not respond in the same way as your European participants would do to that question and to that situation outside of your control. Another one would be the number of participants being too small. That could be a threat to your external validity as well. But what is a large enough number? I've been asked this question already over the break as well, and it's a really hard one to answer. It depends really on the type of research that you're doing. Are you utilizing a within or a between subjects design? Are you doing an exploratory study or are you replicating another study? Are you doing a survey or are you doing an experiment, etc., etc. It depends on all these kinds of factors. But for experimental research, the general rule of thumb, again, this also depends on your design and the type of analysis that you need to run, is that you need about 30 participants per condition to be safe to say that you can generalize your results to a larger audience. But be warned, probably some of you have already realized it, that most of the time when designing your experiment, you have to make compromises because the steps that you take to ensure internal validity often have negative consequences for external validity and vice versa. So you have to really decide for yourself, what is the most important thing here for me to be able to answer my particular research question and why? Again, you have to be able to build like a really good argument for why you make the choices that you make, why you include certain conditions, why you include certain questions, and why you exclude other ones. So I'm going to give you a couple of examples of the kinds of choices that you might have to make in terms of compromising your design. So there's nothing wrong with that, just to make that clear, that you have to compromise your design. Obviously, I am studying people being absorbed in a text in the lab because I want to have sort of all of the other factors controlled. So the only way for me to do that is to get them to the lab and let them read it here. So as long as you make clear why you made that choice, that's good. Okay. So a couple of examples. For example, if you conduct an experiment on the internet, if you do an online survey, this might increase the ecological validity. People don't have to come into the lab. They're not as aware of the fact that this is an experiment. They feel more at ease in their own homes or in any other environment in which they might do the survey. However, it also takes care of the fact that you have less control. You don't know where they're doing this, if they're sitting in a quiet environment. You don't know. With some surveys, you have some control over this in terms of there's timings, so you know that they finished it within an hour, or they started it on this day and they finished it on that day. But sometimes you don't know that either. So to increase, so to say, your ecological validity, you're sort of decreasing the amount of control you have. So that's what I mean with making compromises. Another example would be questions about comprehension. So you want to make certain that people understand the task that they're doing, or that they're understanding the stimulus that you're using. So you're putting questions about comprehension in there. So it gives you more control over whether or not they participated in the study. However, these kinds of questions are also very sensitive to social desirable answering. People will always want to sort of come across in a nice way. They want you to think that they're intelligent. They want you to think that they are very empathic. So these kinds of things are very sensitive to social desirable answering. There was a topic that we talked about earlier as well at our table, social desirable answering. There are ways to sort of deal with that as well. There are, for example, scales that you could use to capture social desirable answering that you could use in a design as a control factor. So you would use this scale and you would find out if they score high on this, they are prone to social desirable answering. If they score low, they're not as prone. And then you take that sort of into account in your design. So if they score high, you might want to sort of take their answers on the other questionnaires with a grain of salt. Okay, so the last example would be the repetition of the same questionnaire within one experiment. Sometimes this is just plain necessary. It could be used for a better understanding, to get a better understanding with the participants of what you ask of them. So you want them to really understand what you're asking of them. So that might help when you ask the same questions twice. Sometimes it's really necessary in the sense that you are, for example, studying rereading. So you need to have like the same questionnaire twice. Thank you, Felix. Sorry, he's closing the door. But it might have the negative consequence of the fact that you have more threats to external validity. There's a higher chance of there being test effects in your results. Okay, so these are a couple of examples of the kind of compromises that you might have to make when designing your experiment. Then the last form of validity that I wanted to talk about was construct validity. This is a very specific form of external validity. It's the validity concerning your measuring instrument. It's about how you translate elements in your conceptual model, your dependent variables mostly. Those are the ones that you're going to measure. How do you translate them into measurable variables? How do you operationalize them? Construct validity is also the most debatable form of validity in the sense that interpretation of even the most simple terms can strongly vary between different people, between different research areas, between different disciplines, between different scholars that study the same thing but have a different understanding of it. And And you have to always be aware of the fact that the manner in which you ask your questions affects also how you can analyze them, so what you can do with them in terms of analysis. The most surefire way sort of to deal with this type of validity is to use established measuring instruments. So instruments that have been used before, that have been tested, that are reliable, that are valid, and have been used in studies over and over again. Sometimes that might not really happen. You might be doing exploratory research into an area that doesn't really have a lot of established measuring instruments yet, and then there are ways of dealing with that as well. The most important thing, again, would be to do your research well, give very clear definitions and very clear arguments about why you use the kinds of questions that you used. I think that is always the most important thing. You really have to be very clear and have a very good argument for the choices that you make. Okay, so that is it so far for the notion of validity. Are there any questions about that so far? No? Okay, then we're going to see how well you listened. I want to put a little assignment in here. So does everybody have the Mangen and Kuiken study with them, or at least one person at each table? Okay, great. I want you to take 5 minutes and discuss amongst yourself the design of Mangen and Kuiken and whether there are threats to the validity of their design there, whether you see possible threats to their validity, and whether you see ways in which the authors try to deal with these threats. And we're going to discuss that in a minute, and I'll give you some hints as to where you should normally look, but I would sort of like you to try it out first on your own. So I'm giving you 5 minutes, and then we'll check back in. Yes, so this is actually a really good point that you bring up, because this is something that we always stumble upon. For some reason, but I think it's pretty self-explanatory as well when you think about it, is that there's always more women in these kinds of samples than there are men. But that's also probably because more often than not we use our students, and students in literature or within the humanities and students in psychology, like the bigger amount of them is always female. So this is a kind of threat that you don't have any control over. But the way in which you deal with this is randomization, in the sense that you randomly assign them to the conditions. So that in that sense, if it has an effect, it's a coincidental effect, and it's not an actual confounding variable. But this is one of those things that I think you have to make compromises somewhere. Like what you shouldn't do then is to see, okay, I've run my study and I see that I have like 80 over 100 participants, I have 80 female participants and 20 male participants. Okay, now I'm going to look for 60 more males, drag them in here and do the same experiment, because that would also influence sort of the results. So that's just one of those things that you can't really control for, but which you would have to sort of point out as well. So, okay, these are the results that we found. We think they're generalizable as far as it goes, sort of, meaning that yes, there were more females in this sample, so maybe we should do follow-up experiments, try to see if we can find more males to do the same experiment. That is usually how you see people deal with that as well. So that was like a really good clue as well. Places to look for these kinds of things would always be the method section of the research paper and then the general discussion. If it's a good article, like this article that we're using here, the authors will already put in sort of lines in the general discussion about, okay, these are the flaws that we saw in our design, or the things that will sort of came up while we were running our experiment, and this is how we chose to deal with it. And these were the kind of unavoidable things that happened that we were not able to control, but which we think would be a perfect place to start to do like a follow-up experiment. So I think I put this page up here because... So, for example, what they say here, in the present study, the intangibility and transient quality of a digitally displayed text may have hindered the representation of such spatial information. So they're very open about like things that might have influenced the experience or might have influenced the results of the study, and they put that in their general discussion for people to sort of to see and build up on that in a possible replication study. I think that was it very hard to find these kinds of things? Because usually when like a mark of a good paper is that you can find these kinds of things, that they're very clear in the method section about the choices that they've made, and then the sort of unavoidable influences that they had to deal with, they will point those out in the general discussion, and they will give either an explanation of how they think that might have influenced their results, and often you also see sort of suggestions for further research that might go in that direction. Okay. So if there's no more questions about validity, then we are going to dive into statistics. I was kind of expecting now everybody to be like, okay, then I have more questions about validity, because... No? Okay. Oh. Okay, so theoretical principles for statistics. I'm putting this slide up here, even though there's a session tomorrow that's called Descriptive and Inferential Statistics. So that's where we're going like very much into detail concerning these two types of statistics. I'm just putting it up here now to say that all of the sort of theoretical notions that I'm going to discuss in today's lecture are all necessary to be able to do inferential statistics. So this type of statistics. Very briefly, because I'm going to go back into it tomorrow, descriptive statistics are there to describe your data. Inferential statistics you use to generalize beyond your data. So inferential statistics are test statistics. And for that kind of statistics to sort of be able to pick the right statistical test, you need sort of some theoretical knowledge underlying it. And that's what we're going to discuss in this session. So here's a short overview of the key terms that we will go through in this lecture. Very quickly. Empirical research is based on the assumption that making mistakes is inevitable. Constant errors that potentially bias your results cannot be eliminated, but they can be controlled for as much as possible by turning them into random errors. How do we control them? We try to ascertain what the probability is that the effect we found was caused by random errors, and that upon replication of the study, it could be caused by random errors again. When this probability is small enough, your results can be called significant and generalizable. Or to put it in a different way, then the probability that the effect you found is due to your independent variable is big enough. To help you decide whether this probability is small enough, you can use the so-called region of rejection. In this area of the data distribution, you can accept that the independent variable had an effect on the dependent variable. That's basically all there is to it. But that was very fast. So now I'm going to go into excruciating detail on every one of these things. But that is basically the story of the presentation. And now I'm going to take you through it step by step. And I'm seeing people like making pictures and like scribbling furiously. They will all be put onto the internet. So no worries. Like if you are, I don't know, going not fast enough. And if I'm going too fast, then please tell me. Like, please wave me down so that I can slow down. If you have any questions, please interrupt me. Okay. So, errors. In methodology, a distinction is made between constant errors and random errors. Constant errors are systematic of nature, and they potentially bias our results, making our outcomes impossible to interpret. For example, say you want to study the effect of digital devices on reading comprehension, which I know is a topic that a lot of you are interested in. And you decide to compare two groups of children. One class from Frankfurt, they are reading on an iPad or a tablet, and one class from Göttingen, and they're reading from paper. If you then find a difference between these two groups, can you conclude that there is an effect of the digital device? I see a couple of people shaking their heads already. Why not? I hear different places. Yes. You cannot conclude this because apart from the fact that they read from different devices, so one group reads from an iPad and the other reads from paper, they also enjoy an education in a different place. So the effect that you found might actually have been due to a difference in the way that they are taught to read and not due to the device that they used. Now, I think this example is pretty clear. Often, though, it's very hard to detect these types of constant errors, especially if you have a more complicated design than this. In the example that I just gave, educational program, if you will, would be an intervening variable, and those usually count as constant errors, if you do not take them into account, that is. If you take them into account or control for them, you do not eliminate the error altogether, but you can transform them into random errors or covariates. Now, the assumption that we will always make mistakes is not strange per se. However, it does change the way that we run statistical tests. So with statistical tests, we do not test what the chance is that our independent variable had an effect on our dependent variable, but what the chance is that the effect we found was due to random error. So it's kind of a little bit roundabout, but it's the only way in which we can take our errors into account in our analysis. That's basically what the first line says there. So a key notion in this whole picture is probability. To repeat, we investigate the probability that our unavoidable errors cause the effect on the dependent variable. I'm going to repeat this a lot. So if you get sick of me, also wave me down, but I think that's really the best way to sort of get it into your system, because it's kind of a backwards way of thinking about it. So I think it's good to repeat it a lot, but if you get sick of me, just let me know. If the probability is low, we can assume that the effect on our dependent variable was caused by our independent variable. So by taking a little detour, we eventually do arrive at the relationship that we're interested in. Okay, then within statistics, probability, or P, is signified by a number between 0 and 1. So this P here, this is what we call the P-value, and it should also always be reported cursively, if that is a word. That is a word, I think. Sideways, I don't know. So a number between 0 and 1. The 0 would mean this never happens. A 1 would mean this always happens. I'm going to tell you now, you will never find a 0 or a 1 in your statistical, in your output, sort of, in your outcome. And if you come across a p-value in a research paper, it will always be sort of written down like that. So p cursively is, and then a number that starts with a point, and then usually 0 or hopefully 0, 3, 1. This is an example, obviously, but it will always be sort of reported in this manner. You can turn such a p-value into a percentage of probability, which is easier sort of to work with, by just sliding the comma 2 decimal points to the right. So a p of 0.031 is a 3.1% chance that this effect was caused by random errors. So that's good. That's a very low chance. That's good. To put it in a different, to put a different perspective on it, we could also turn it around and look at it slightly different. So if p is 0.031, we are 100 minus 3.1% is 96.9% certain that our results are generalizable to the general population, that they were not due to random error, in other words. Thus, the lower the p-value, the more certain that we can be about our results. So actually what we could say is that the p-value represents the chance that we falsely conclude that the independent variable had an effect on the dependent variable. Is everybody with me so far? Yeah? Okay. When is the p-value low enough to assume that the independent variable had an effect on the dependent variable? To be able to answer this question, first we have to rephrase our research question into a testable hypothesis. The hypothesis in inferential statistics or in empirical methods always needs to be concerned with a difference between groups. It should be formulated as such. There is a difference between group 1 and 2. This would be your H1, your hypothesis 1. You should also be able to formulate the logical opposite of this H1, which would be your H null or H0, namely that there is no difference between group 1 and 2. For example, and I'll take the case study of Anna. The research question, do readers who read a fiction text on an iPad report different levels of transportation than readers who read the text on paper? Could be formulated into an H1 in this manner. There is a difference in the level of transportation between iPad readers and paper readers. The H0 would then logically be there is no difference in levels of transportation between iPad readers and paper readers. Just to be clear, if you're working with a within subjects design, you can still do this kind of hypotheses formulating, but then the difference would not be between two different groups of people, but between different instances in which you measure the participants. So like time 1 and time 2. Okay, why do we need these specific hypotheses? What we do is in empirical methods or in inferential statistics, we work according to the principles of falsification. So what we try to do first is we always try to reject H1, the hypothesis that there is a difference in level of transportations between iPad readers and paper readers. If that fails, we should logically reject H0, or we should need to reject H0. In other words, we reject the hypothesis that there is no difference and therefore assume that there is a difference. Again, this is a very roundabout way of doing it, but it's the proper way of doing it. If we can reject H1, we logically need to accept H0 and therefore that there is no difference. Is that clear so far? Okay. In order to determine whether we need to reject H1 or H0, we need probability. And thus we come back to the question, how low does the p-value or the probability value need to be to reject either hypothesis? Actually, there is no unambiguous answer to this question. There's no ultimate rule. Because random errors will always remain, we cannot really eliminate them. We are instead working with a sliding scale, if you will, with various numbers on it that give us information about the likelihood of error occurring, but the numbers in themselves do not really tell us much. They do not contain an indication as to when to decide that the error probability is low enough. Luckily, there are some conventions agreed upon within statistics that can help us decide in these kinds of situations. As a researcher, what you do is you choose your own level of probability that you decide is acceptable, and that is then the probability level to which all of your p-values need to adhere. This level may vary between projects. So you might want to be more lenient, for example, when you are conducting an exploratory study, which has never been, like a topic that has never been researched before. You might want to be a little bit more lenient with your probability levels. However, if you are replicating established studies, you may wish to be rather strict, or in any case, at least pick the same probability level that the previous studies have used. We call these sort of error probabilities significance levels. Significance levels are always signified with an alpha in statistics. Like I said, the alpha is not fixed, it's determined by the researcher. However, there are kind of 4 different levels that are most often used in statistics, or in our field, sort of. I'm not really sure, I'm not an expert in statistics at all, but I am talking now about the field that we would all be sort of working in if we would do empirical research in literature studies, media studies. So these are kind of the levels that are used most often in the fields that concern us. It might be completely different when you're doing, I don't know, biomedical stuff, but I have no idea about that, and I don't think that would be interesting in any case. So the 4 levels that are sort of accepted, that are used most often, are the 10% level, so that would be a p-value of 0.10. 5% level, so that would be a p-level of 0.05, 1% level, 0.01, and then the last level is usually not even indicated as a p is, sort of, but as a p is lower than 0.000. Okay. So for example, again, if you are investigating the difference in transportation levels between iPad readers and paper readers, and you set the significance level at 0.05, since that is the level that is most commonly used within that field, and your research is building on other studies that have done similar things before, and you see that they are all using this particular significance level, and you find a difference with a p-value of 0.031, you could say that the difference in transportation levels between iPad readers and paper readers is significant because it falls under your designated significance level. However, if you had chosen a significance level of 0.01, your results would not have been significant. It goes without saying that you have to choose the significance levels first, and then only accept those that fall below it, and not do it the other way around, like just do the analyses, see what comes out of it, and then set your significance level at a level where you're like, yes, now I have significant results. Obviously, also, there's a certain arbitrariness to this. So a p-value of 0.049 would be significant, but a p-value of 0.051 would not be. That's kind of arbitrary. I will come back to this later on in the presentation. For now, we just have to accept that we have to set some rules to be able to interpret our results. And in some cases where your results fall on the border between significance and non-significance, these rules do seem rather arbitrary, but that's just the way it is. Okay. As I said, the choice for your significance level may vary between projects, and there are two risks that you need to be aware of when you make your decision for your significance level that you're going to use. Type 1 errors, they occur when you choose a significance level that is too high, which may lead you to allow too many random errors. Type 2 errors can occur when you choose a significance level that is too low, which may lead you to miss out on effects because you are too strict. So type 1 errors then lead you to falsely conclude that your independent variable had an effect on your dependent variable, whereas actually the effect was caused by random errors. Type 2 errors lead you to falsely reject H1, whereas actually you should have rejected H0. So you have to be aware of these risks to the choice that you make in terms of significance level. To avoid these types of errors, luckily there is a kind of sort of general unspoken consensus, and that is that we work with an error probability or significance level under 0.05. That's like the most often used significance level. So results with or under a 5% error probability we would call significant. Significance in this case would mean that your results are generalizable. If the p-value is below 0.05, you can reject your H0, that there is no difference, which means that there is a difference between your groups and that the difference is significant enough to be able to generalize your results to the general population. Everybody with me? Yeah. So, and then the question is, I'm just going to repeat it also so that like everybody hears it on the recording as well. The question was, what falls under random errors? Is that intervening variables? Is that, what else did you?
The ones that we might don't know about, or that
Yeah.
we missed out because we didn't ask about them, or that we just don't have any control.
Yeah, so all of the variables that we don't have any control over. The basic answer is yes. So those can all fall under there. And it's kind of what Berenike also tried to tell you this morning, and what I also started with as well, is that you have to try to sort of control for as many of these possible intervening variables as possible. But then still, there's always something. You can't possibly account for everything that might influence your experiment, the results of your experiment. That's also not really the goal in the end. That would make it impossible to ever start running an experiment if you try to control for everything that might have an influence. The goal is to try to make an as elegant, or how did you put it this morning, a simplistic elegance? Yeah, to make it elegant simplicity. Try to make it as elegant as possible. Try to account for as many of these possible intervening variables that you can think of. And then obviously there will be random errors that slip through, and that's what we are now sort of, within statistics, we can account for the fact that there's probably things that you haven't thought about. And those are the random errors, the things that you couldn't sort of, you couldn't control for it within the experiment. So in a sense, the statistical testing tries to sort of not completely solve, but at least take into account the fact that there's probably some errors that you made in designing your experiment that you couldn't account for, and it tries to sort of steer your results in the right direction, if it were. Yes, so that's a very good point that Berenike makes. So maybe it's easier to not, or easier, it's not only that there's an effect of errors, it might also just be that there's an effect of pure chance. Like that could be an intervening variable as well, or that could be something that influences your design. It's not necessarily an error on your account, but just the fact that something happened by pure chance, and you could never have accounted for that. So it's not, maybe that's a nicer way to put it, like not putting it on you, as in you are going to be making mistakes because that's what you do, but saying there's a lot of things that are up to chance. So to help you determine whether to reject your H0, your null hypotheses, you can make use of what is called the region of rejection. So with the acceptance of a conventional level of significance, that leads sort of to a separation between areas in your data distribution. One area in the data distribution is the area where only random errors had an effect. That area is called the region of rejection. And then there's an area where the independent variable had an effect on the dependent variable, which would be the region of non-rejection. The region of rejection is based on the significance level that you choose. I'm going to show you a visualization of it to make that more clear. So here you can see a visual representation of a data distribution. This is what we call a normal distribution. This line here, that's basically the distribution of all of the data points in your sample. And if it has a nice bell curve to it, that's what we call a normal distribution. But I will go into the normal distribution in detail in tomorrow's lecture on descriptive and inferential statistics. For now, basically what you have to imagine is that this line represents the mean distribution of all of your data. Let's say it represents, for example, people's transportation levels. So most people, when they score an item on a scale from 1 to 7, they score around the mean. So that is the peak of the bell, so to say. And then there's always a couple that score way higher, and there's always a couple that score way lower, and those are in the sort of tails of the distribution. The critical value here that determines the region of your distribution is your chosen significance level. So for example, the 5% level. In the area of distribution that we call region of rejection, so that would be the blue area, so the tails of the distribution, we accept that the independent variable had an influence on the dependent variable. We do not know for sure, but the likelihood that we are mistaken is low enough to accept this conclusion. It is lower, for example, than 0.05 if that was the significance level that you chose to work with. And then if your p-value lies in the non-rejection region, you cannot prove that you have to reject H null. Okay, so to sort of briefly summarize, inferential statistics is all about the question of how confident we can be in generalizing from our sample to a larger group. So for example, if you find that in your sample there is a difference between iPad readers and paper readers in how much transportation they experience with a p-value of 0.031, this p-value tells you that if you ask another two groups to read the same text on iPad and on paper, there is a 97% chance that you will get a similar response. That's another way of looking at it. So here you see two regions of rejection, or there's always two regions of rejection, but in this case, we also look at two regions of rejection. Sometimes there's only one region of rejection that is of importance. So whether you have two or one regions of rejection is dependent on how your hypothesis is formulated. In essence, your hypothesis, your H1 that is always about a difference between groups, like I explained earlier. But it does not necessarily need to include a direction of the difference. So for example, your hypothesis can be there's a difference in transportation levels between iPad readers and paper readers. That would be a non-directional hypothesis. Your hypothesis could also be iPad readers exhibit higher transportation levels than paper readers. then it's still about a difference between the two groups, but you have also indicated what you think that the direction of that difference is going to be. You think that the iPad readers would score higher than the paper readers. Now, this is also something that we have to be clear about before we are going to run actual tests. So we can know whether our region of rejection lies on both sides of the data distribution or just on one side of the data distribution. What we call this, and that's based on the fact that we have this normal distribution with the tails, we call this either a two-tailed test, so that's when you have no direction, or a one-tailed test when you do have a direction to your hypotheses. Okay, if that is all clear, I have another assignment for you. Again, we would look at the Mange and Kuiken text. And I would like you to go to the results sections and read through some of the results together, and then try to make sense of the p-values, for example. What do the p-values mean? How should you interpret them? Of course, the authors have also given their interpretation, but make sure that you are very clear on what these p-values, what they actually are saying, what they mean. So I give you another 5 minutes for that, and then we will go on. I don't think there's a lot left in the presentation. Yeah. Okay. Marginally significant results. I'm so glad you said that because that's the next slide. Okay, I need to go. No, I'm going in a different direction. So one thing that I told somebody just now is that, no, sorry, I'm just going to put the right slide on. Okay. So one thing that I want to share with you is that if you have problems sort of grasping these principles, because it is like I said, it's a pretty roundabout way of doing things, and sometimes it gets really confusing when you start to think about it in this way. So the book that really helped me with that is Andy Field's Discovering Statistics. This one he wrote for discovering statistics using R, but he also has one that he wrote where it's discovering statistics using SPSS. That one is also lying in the kitchen. And this is a really well-written, funny book that is specifically written for people working in the humanities and in social sciences. And it has very clear examples, and it explains these kinds of things in a very clear way. And I understand that this is like a pretty short period of time in which to sort of cramp all of these things in your mind in the course of 3 days. So if you're looking for some good resources to sort of practice these kinds of things, Andy Field is sort of, yes, Andy Field. This is also, I'm going to put a list of resources and references that I'm referring to in the training school. I'm also going to put that online on the website and email you about it as well. He has a really great website as well. It's called Statistics Hell, statisticshell.com or something like that. And he has YouTube videos on there in which he shows you how to do all of these different tests with SPSS and also with R. And in which he just explains basic principles of different tests and stuff like that. And for me, this really helped, this book, to sort of wrap my mind around the more difficult aspects of these kinds of things. Okay, having said that, let me see. So yeah, words of warning about marginally significant results, amongst other things. Like I said before, there is not much difference between a p-value of 0.048, which would be significant, and a p-value of 0.052, which would be non-significant. So what I would like to stress is that you shouldn't be too mechanical when you're using a significance level. So p-values that are relatively close to your significance level, but that are technically not significant, do show a tendency towards significance, or are marginally significant. That is also a term that has been used. And I would say do not discard your non-significant results immediately, especially not if they sort of are showing a tendency towards significance. Also, but this is more of a personal opinion on the matter. I think that research is not only valuable when it is significant, especially because we base this whole statistical testing on the assumption that we make mistakes, that making mistakes is unavoidable. I think what comes with that is also that we should learn from our mistakes and from the mistakes of others, and that therefore also non-significant results, because they're due to mistakes or because they're due to something else, are very interesting. However, as the current state of the field shows, it's really hard to value your own results if academia is so focused on publishing only hypotheses confirming and significant results. Luckily, there are some suggestions that have been made and that have even been taken up on by researchers in the field, such as the pre-registration system that journals could use, like papers should be submitted and accepted or rejected before the results are even in. So that they are evaluated based on the strength of their design, the validity of the measures that are used, the innovative nature of the research question, but not necessarily the results that come out of it. Basically what I want to say with this is that I think that we should not sort of hang our hats on the p-value, even though that's sort of the principle that we're working with. Don't get too mechanical with that, and don't panic when your results are non-significant, because that's going to happen a lot. You will find non-significant results a lot, but it's not to say that then they're not interesting anymore. There's a lot of non-significant results that tell you a lot about the topic that you're researching. So yeah, that's kind of like a message that I want to send you home with. And that was actually it for this particular session. And I'm wondering whether there are still any questions left.